Hi, I'm Casey Stewart, and today we will be presenting from the Principles of Polymer Systems 5th edition book. We will be presenting problem 8-9, and with this problem, the problem states, as a polymer can be represented by two Maxwell elements connected in parallel, each with the same spring modulus, in a stress relaxation experiment, the stress is decreased to 23.7% of the initial value after 10 minutes. If the relaxation time for the first element is 10 minutes, what is the relaxation time of the second element? And with this, we can start it off by looking at a model of the system. For a Maxwell element in parallel for two different elements, we're going to end up having something like shown. Here we're going to have it where instead of this system, we're actually going to go the opposite direction, where we're going to start with the known stress, and instead we're going to work our way kind of back towards zero. So we'll kind of have an opposite situation from given here, but it's at least a general outline of what to expect and like what we will be using for the calculation. With this, we're given certain different things, and we're starting off with, we're given at time zero, we have the full stress. This is known with the system being a stress relaxation experiment. Outside of this, at the time for 10 minutes, we have 23.7% of the initial stress. And then outside of this, since it's a Maxwell element and the same spring modulus, we can conclude that the elongation and Hooke's law are going to both end up being the same for each element. With this, we can go forward and we can draw from equation 8-80 out of the book. With this equation, we can use the fact that the stress is going to be the sum of the elongation times by Hooke's law times by the exponential of the time divided by the relaxation time for the respective element. So with this equation, we can show that the total time is dependent, the total time dependent force is equal to the force acting on it. With this, we can also use the fact that Hooke's law is going to also be used with viscosity to be able to find the stress in other scenarios if you're given viscosity. And then the other thing to note is using Hooke's law and elongation, we can end up finding the stress. And in reality, with two different elements, we have it where it's going to end up being the two add up to equal the stress. So it will end up being 2 times by the elongation times by Hooke's law. With this, we can now continue. We can use our work, and we can start off where at time zero, we know that it's going to be e to the 0 because the time is on top. And with this, we can end up figuring out that the elongation and Hooke's law are going to end up relatively both being equal to 1. So when you have 2 times that, it's going to end out equaling to 0.5. We can now factor that out and bring it to the other side of the equation to change the equation to where it's stress divided by elongation and times by Hooke's law to just end up with our time and our relaxation times on the right side of the equation and then the rest on the left. We can now implement the numbers for the time of 10 in order to be able to solve for this. And at time of 10, then we can figure out it's 23.7% of the initial, so we can input that value. We know that it's 0.5 for the value of the elongation times by the Hooke's law, and then we can end up having it still be equal to the exponential of the time over the relaxation time. Here we can also implement the fact we know that the relaxation time for the first element is time 10. So now all we have left to solve for is the relaxation time for the second element. With this, we can now continue down and break it down. When you divide by the 0.5, you get it down to 0.474. And then when you get rid of the e to the negative 1 and bring it over to the other side of the equation, you're just left with 0.10621 to the exponential of the time being 10 over the relaxation time for the second element. With this, we can times by the natural log of both sides to end up changing it and getting it out of the system. And with this, we end up putting it where instead we end up with negative 2.27671 equals negative 10. Divide by the relaxation time to that second element. And with this, you can solve by multiplying it to the other side and then dividing the 10 by the 2.2761. And you're going to end up with the time being about 4.458 minutes. And that's going to be where you finish this problem. But here we can also say thank you to Rheology Theory and Application to Biomaterials for the amazing slide to show the module.